Okay, here we go, Kinematics and Mechanics section of our practice act. We're going to examine some questions and work through some solutions. Let's go. Alright, so let's have two bodies of mass A, which rests on a horizontal table, and mass B, respectively, are connected by a light inextensible string. There it is, passing over a frictionless pulley, as illustrated below. So there we go, that meets all the requirements, just to make simple assumptions of tension in one part of the string being the same as tension in the other part of the string. Now the coefficient of friction between mass A and the table is given by our mu, our coefficient of friction. So first off, let's clearly label all the forces on the system. There we go. So we've got a normal force, we've got force due to friction, we've got a weight force, we've got tension. And on mass B we've got equal size tension and a weight force. So if A is 8 kilograms and B is 1 kilogram and we have a value for mu, find the resultant force on the system in newtons and the acceleration. Okay, so considering the first mass, we're going to break it down into the I component, the horizontal component. So the sum of all the forces is mass times acceleration. So adding it up, we've got negative friction force plus tension force, and in the J component, the sum of the forces equals mass times acceleration, and we have Newton, the normal reaction force, subtract the weight force, and that's going to equal to 0 because there's no motion in the vertical direction, only horizontal. Alright, now from that expression we're able to see that the normal reaction force is equal to the mass times gravity, its weight force. It's a reaction force, so equal in opposite direction. Now let's examine the second mass. Now it only has a vertical component, so let's sum all the forces up, and we've got a tension, subtract the weight force, equals to a mass times acceleration. Now what's important here, have a look, is a negative in the front of the acceleration. So it's saying that it will go down, it will accelerate downwards. Okay, and so the force, the direction downwards is negative, and so the acceleration will be also negative, okay, in this system. So for a mass of 1 kilogram, we get this for tension, okay, by substituting 1 in there for the mass and solving for T. We've got a G subtract its acceleration that it will experience when the system moves, and B block moves in the downwards direction. So we're going to use this equation, it's number 3, we're going to now combine some equations. So we're going to sub equation number 2, which is this one, and equation number 3, which is this one, back into the original equation number 1. Okay, and so the value for N and the value for T, and we substitute our values for A, the mass of A, and the coefficient of friction, and we can solve for the acceleration, and we get G divided by 18 meters per second squared. Very good. Let's move on. Alright, so now from that let's find the tension in the string. Well, from this equation, equation number 3, we established that the tension is the gravity subtract the acceleration that the system experiences, where the acceleration was the amount that we calculated, the G divided 18 meters per second squared. So let's use that value, substitute it in, and simplify, and we get 17 over 18th as a fraction of our gravity in newtons. So you can use 9.8 and multiply that out, 17 times 9.8 divide 18, and express your answer in newtons. Alright, now let's think about it differently now. What would be the minimum value of mu required for the system to be in equilibrium? Right. Wow, equilibrium, what does that mean? Well, you got to keep in mind equilibrium is when all the sum of forces, your net resultant force, balances out and equals 0. So that means the acceleration is 0. System is stationary, it's not moving. Now, we got to take that into account on both masses, because on mass B gave us equation number 3, but this is for when the system does have acceleration. So now, for an acceleration of 0, we get the tension changes. The tension is just equal to G in newtons. And so coming back to our original equation number 1, there it is. Now, acceleration has to equal 0, and our tension is G newtons. So we substitute those values in, and now the only unknown is mu, and we're going to solve for mu, and we get 1/8. Very good. So you have to, whenever we get a particular scenario given to us, such as the system's at equilibrium, you have to consider how that affects the motion on all masses in the system, and look at the equations of motion for each mass. Very good. Okay, let's keep going. So a block of mass m is on a surface with a coefficient of friction mu that's on an incline of 45 degrees to the horizontal. And this mass here is subject to another force P. It could be a pulling force, or it could be a tension force, or a driving force that drives it up the plane. Now, our mass is about to move up the plane. So it's on the verge of motion. Okay? It may have reached its maximum static friction. It's maximum static friction. So, first off, let's label all forces on the diagram. Alright, so they're the forces on a mass on an inclined plane. P is also a part of that, but that's already labeled. We don't need to label that one. Now, they are all real forces acting on the mass, and the ones on an angle to the direction of motion on the plane, well, they have components, but they're not real forces. They're just components of our, for instance, the weight force mg. That's the real force there. All right. So, setting our orientation, because it's moving up the plane, we're going to say this direction up the plane is positive I direction. And from that we can identify the components of our weight force. There they are. Alright, so let's draw on that. And part B, in terms of mass m and the mu coefficient, what is the minimum value of P needed to move the object up the plane? Okay, so the motion of the block has competing forces. It's got a friction that's opposing its motion. You've got acceleration due to gravity, which is pulling it down the plane, and so we need a force P that's going to balance out that forces and exceed them to move up the plane. Let's find that minimum value. So we consider the equation of motion in that horizontal direction, in the I direction. P subtract mu times n, subtract the component here. And that has to be greater than 0, so it starts to move in that direction. Alright, so there's our first equation. Now, vertically, we see that the normal reaction force balances out with the cos component of the weight force. So we get this expression for the normal reaction force. Very good. Let's substitute that back into equation number 1. And now let's transpose for P. And P has to be greater than the mass times the gravity of this expression involving sines and coses. Let's evaluate them. We've got a common factor of root 2 on 2. Let's take that out, and we get this as our simple expression. Okay, so the next part, if the mass, we're told, has this value, 10 root 2, maybe kilograms, and mu is 0, so that means we've got a smooth plane now. It's no longer friction is involved. The object starts from rest, and the force P is given by the rule P is equal to 20 minus 10t. So it's a non-constant force. It's a force that changes as a function of time. And our job is to find the resultant force on the block and the acceleration at a point in time. Alright, so again, let's add up all our forces. Alright, and evaluate our sine function and substitute values for mass, and we get that. Now this time the value for mu is 0, so this term here, that gets cancelled out, that goes to 0. There's no friction in this example. Simplify it a bit, there we go, and we can express that neatly in a linear fashion by collecting the constants and putting a bracket around them. And there's the resultant force in newtons. Now relate that to mass times acceleration, and retranspose for the acceleration and simplify it. Any common factors, bring them out of a bracket like so, and there's our acceleration as a function of time in meters per second squared. Excellent. So from that, the next question, find the velocity. We have to find the velocity of the block and the change in displacement of the block at any point in time. So how does, from acceleration, how does velocity and how does displacement relate? Well, you got to draw on calculus, and it's in fact the antiderivative of acceleration gives us the velocity. And drawing on the idea, we were told that the object starts from rest. That means at the start of time, it's at rest. It's not moving, so that means its velocity is 0 when time is 0. So that's what we call the initial condition. So let's set up our integral. And we're integrating a linear term and a constant term. Now this factor of root 2, well, that doesn't take part in the integral process. You can almost imagine it's not there. You can bring the factor out the front of the integral sign and just focus on the terms, the t terms and the unit terms, okay, because that's what we're integrating with respect to, t. Alright, so we add 1 to the power and divide by the new power. There we go, that's what we get. And don't forget integration constant plus c. And now let's use our initial condition. When t is equal to 0, velocity is equal to 0, and that gives us c is equal to 0 value. So there's our velocity function. Now, the next part is find the change in displacement. So how does displacement relate to velocity? Again, that's the antiderivative of velocity. Gives us our displacement. So let's set up the integral. Okay, again, we're integrating with respect to time. So the root 2 factor doesn't take part. You can think of it as a factor out the front of the integral, and it just stays as is. So we're integrating the terms inside the bracket. Okay, so again we add 1 to the power. So 2 plus 1 goes to 2 to the power of 3, and we divide by the new power. So we've got a 4 times 3 in the denominator, gives you a 12. Now have a look, the little numeracy applied here. I've got 5.1 as a decimal. Now that is a 51 divide 10, and then when we integrate, we add 1 to the power of t and divide by the new power, so we're dividing by 2. So the 51 on 10 becomes a 51 on 20. Got to be ready to convert decimals to fractions to express them more neatly when necessary. Alright, so now let's apply our initial condition. It's starting from some origin position, so when time is 0, the displacement is 0 because it hasn't moved, and so we get the integration constant c is also 0. Therefore, let's express our displacement function in full. There it is. Okay, how'd you go with that? Let's look at the next part. So now, a body of mass 4 kilogram rests and it's not moving on a sloping surface inclined at 30 degrees to the horizontal. Now it is subject to a pulling force P that is also inclined at 60 degrees to the surface shown here. So we've got two lots of components to consider. Now the coefficient of friction between the mass and surface is this third. Okay, so it's a rough surface, and we need to take into consideration our friction. Okay, so if the block is stationary, but on the point of moving up the plane, okay, so it's at the full extent of its angle, such that if you increase the angle just a little bit more, it will start to move. So we've got a maximum static friction. So there's our forces. Our normal force, maximum static friction, has the value of mu times n, and the weight force. We've also got force P, but that has its components. So there we go, we can set up the direction that way because we're moving up the plane. So positive I direction up the plane, and we can set up our components. Okay, so now let's see if we can find the friction force in terms of P. P being the applied force that's pulling up the plane. Okay, now let's look at the I component of the equation of motion on the mass. So the sum of all the forces are going to be the cos component of P, there it is, run next to the angle, adjacent to the angle. And we subtract our friction force. We want the friction force as F. So label it as F subscript F, like so. And then the other force is the component of the weight, which is this one here, which is the sine component down the negative. So make sure negative 5g sine 30. Now, because the block is a stationary block, that means, of course, acceleration is 0 when block is stationary. And that's why our equation of motion here is equal to 0, because the sum of forces equals 0 when it's stationary, when it's at equilibrium. Now, from that, we're going to evaluate the sine and the cos and transpose for our friction force. So we will get a P, take 5g all onto in newtons. Hence, let's find P. Now, friction force, if it is stationary, the friction force takes on the formula mu times n. Okay, so that there is the static friction maximum value, where mu is your static friction coefficient. Now we've got another expression for our friction force that we determined. That one was in terms of P. Now also, by looking at the equation of motion in the j direction, we get this expression here. Alright, n newtons up minus the cos component of the weight. Okay, but there's also the sine component of the P force, also in the positive j direction, and it's stationary in the j direction, acceleration is 0. And from that we get an expression for our normal reaction force. There it is. Now, we also know that the coefficient of static friction is given by this third, so that means we've got all the values now for the right hand side of this friction force equation. Whereas the left hand side of the friction force equation, well, that's what we achieved from the previous question. Okay, there it is. That one is from part B, part I. So we put in all our values, substitute them in. Now we've got an equation all in terms of P. So let's expand and simplify our expressions by cancelling out common factors, for instance. Expand the brackets, and collect like terms and solve for P. P equals to 5G, which is 49 newtons. Excellent. Okay, let's move on to part C. Now, if the block is stationary, but on the point of moving down the plane, okay, now think about the direction of our friction force if it's moving down the plane. Now, to help you do that, it's important to sometimes just draw the scenario with the forces acting in the right directions. So now, here, if we're moving down the plane in this way, that's the direction of the acceleration. And then that means the friction force is going up the plane now, opposing its motion. We've got P force going up the plane at some angle, theta, normal reaction force, weight force going down, and so on. Okay, so our job is to now identify what is the P force needed to keep the thing at equilibrium, stationary, and we're going to express P in terms of unknown theta. Let's have a look. Okay, so we start with equation of motion, the sum of all the forces, the resultant force. We have agree on a direction, so if going down, if it's moving downwards, let's say down is positive. So we have positive I, J. So then we've got the positive sign component of the weight force minus the friction force minus the cos component of the P force. And see, cos is in terms of theta. There's our first equation. Now consider the J component. We can work out our normal reaction force. Okay? It's always equal to 0. The sum of the forces is always 0 in the J direction on our inclined plane problems. So solve for N, a normal reaction force, and there is our expression. Sub that into equation number 1. And at the same time, let's put in our coefficient of friction surd number in the equation as well. There we go. And now we expand and simplify. Now we've got common factors of P in these two terms, so let's factorize P out. Outside some brackets. There we go. Let's simplify our G terms, our gravity terms, and subtract the value over to the right hand side. And transpose for P by dividing by this bracket. Now the negative in front of the 5/4 G, well, that negative has been absorbed inside the bracket. So where it was once a negative cos, now it's become a positive cos. And when it was a positive sine term, now it's a negative sine term. And finally, if I just expand my 4 into the bracket, I get this as my expression. So what does this mean, this expression for P? Well, this is the relationship between the size of the pulling force up the plane, okay, and the angle at which the pulling force occurs. Now, this is the pulling force that is needed to maintain equilibrium in the system, so that the pulling force is balancing out the tendency to want to accelerate down the plane. Okay? Let's have a look at a graph of P function as a function of theta. It looks like this. Okay? Where it becomes asymptotic here, becomes asymptotic when x is pi on 2. That's the limiting angle. So in other words, if you look at your little diagram, the P force is this P force on an angle. When P is at a 90-degree angle, it's parallel to the normal. It's coming up this way. Well, that's not moving in any I direction, and so there will be zero motion at all. So essentially, as angle increases, the size of the pulling force also has to increase, and has to increase in such a way to balance out it's the weight force and the tendency to move down the plane. And what's important to note is that there is no stationary points on this graph, in this function. No stationary points. There's no minimum value of p or maximum value of p that you can determine that can keep it stationary. Alright, marvelous. So there we have it. Please review those questions. The SAC will be similar to these, and we did a good job. Well done.